Welcome everyone. This is Jim Steele, and I'm going to separate the science from the pseudoscience that's being pushed regards flood and extreme precipitation in part 7 of how pressure systems control climate. Now floods are the most frequent of all natural disasters. The deadliest of all recorded floods devastated regions of China in the cooler times of the late 1800s and 1930s. But the visible heartache of floods today make lucrative clickbait for mainstream media and good optics to push a climate crisis. For example, last year National Public Radio promoted pseudoscience in order to frame floods as the new existential threat. Now, level ground, rich soils, and easy access to water have enticed people to colonize the floodplains for millennia, despite the risk of inevitable catastrophic floods. Building levees was one solution, but by denying a river access to its natural floodplains, levees amplified downstream flows only to relocate the flooding. This video won't delve into the effects of human levee systems. Here I'm going to focus on the latest science to establish how much flooding can be expected from natural climate variability. Now, due to the inevitable natural frequency of floods, by 1920, private insurance companies in America stopped offering flood insurance. Unwisely, governments then offered flood insurance that has unintentionally encouraged people to keep staying on the floodplains, no matter how often they need to rebuild and no matter how much wetland ecosystems are lost. As seen here, Florida's St. Johns River lost over 90% of its floodplains to encroaching humanity in 70 years. But observing the environmental damage, there are now ongoing efforts to restore much of the wetlands as possible. The advent of the satellite era has now allowed scientists to be able to construct a much more accurate picture of the Earth's precipitation patterns and flood risks from climate change. Kevin Treubert from the National Center of Atmospheric Research is an outspoken scientist who has promoted much of the pseudoscience regards floods, and unfortunately, he is usually the first scientist mainstream media interviews in search of a climate crisis headline. He generates pseudoscience by misapplying the proven Clausius-Clapeyron equation, which states a 1 degree Celsius rise in temperature increases the atmosphere's moisture holding capacity by 7%, and argues theoretically that global warming must then be increasing rainfall and making all floods much worse. But while the Clausius-Clapeyron equation is verifiable in a laboratory, it doesn't explain global precipitation patterns. Now, Nguyen in 2018 published a satellite-based examination of precipitation, and it shows the average rates of regional precipitation around the globe. The trade winds carry moisture evaporated from the relatively cloudless regions, represented here in the dark blue, and concentrate that moisture in the intertropical convergence zone, the ITCZ. Now, the ITCZ is represented here by the darker red colors circumscribing the equator. The ITCZ accounts for about 32% of all global rainfall, and the importance of a shifting ITCZ on wet and dry climates was discussed in earlier parts of this series. Now, if global warming was increasing evaporation, then the ITCZ would be one of the most sensitive regions to support Treubert's proclamations that global warming is causing climate crises and more extreme rainfall. Now, the Western Pacific warm pool is the largest part of the ITC region of heavy rainfall. Yet in the heart of the warm pool, Indonesia's elevation differences illustrate how interactions with cold temperatures greatly affect the degree of rainfall. In Indonesia's lowlands, they receive 70 to 125 inches of rainfall a year, while in Indonesia's higher and cooler elevations, they receive 2 to 3 times as much rainfall. Clearly illustrated here, warmer temperatures simply don't translate to more rainfall. Over the Sahara Desert, where maximum temperatures average 40 degrees Celsius or 104 Fahrenheit, there is only enough moisture to produce 3 inches of rain each year. In contrast, Dublin, Ireland receives over 10 times that amount of rainfall despite a much lower average high temperature of just 15 degrees Celsius or 59 degrees Fahrenheit. Clearly, atmospheric circulation can trump the Clausius-Clapeyron temperature equation. Using 33 years of NOAA satellite data, Nguyen 2018 also mapped the world's trends in precipitation, revealing a vast mosaic of increasing and decreasing trends that defies trend-burst pseudoscience. The blue areas represent increasing rainfall trends, of which only 2.3% of the Earth experiences any statistically significant increasing trend. Regions of decreasing precipitation are illustrated by red colors and cover half the Earth, but significant drying covers twice the area of significantly increasing precipitation. To see more clearly where statistically significant changes are happening, Nguyen 2018 produces this map. And contrary to trend-burst claim that global warming will cause convergence zones of moisture to exhibit increased extreme precipitation, over 95% of the intertropical convergence zone region has shown absolutely no significant change in 30 years, casting serious doubt on the usefulness of either the Clausius-Clapeyron equation or global warming average statistics. And likewise, over the USA, where extreme precipitation events and floods are quite common, there has been no significantly increasing rainfall. In 2011, Michael Dettinger, a hydrologist with the U.S. Geological Survey and a Scripps researcher, published this illustration showing the location of weather stations that report extreme rainfall of 400 millimeters or 15.8 inches or more of rainfall over 3-day periods, spanning the years 1950 to 2008. It is well known that most extreme rainfall is largely associated with hurricanes and atmospheric rivers, and accordingly, extreme rainfall is observed along the Gulf Coast and the eastern coast of the USA during the warm months when and where hurricanes are the most impactful. The purple dots represent weather stations that have recorded one extreme event in the past 60 years, while blue dots represent locations observing 2 or 3 extreme events during that time span. Atmospheric rivers delivered the extreme rainfall events in California, happening mostly during the cooler months of the late fall, winter, and early spring. There are a few weather stations that have recorded extreme precipitation events 6 and 7 times in those 60 years. The water cycle helps illuminate the source of moisture for the various extreme rainfall events. 85% of the Earth's evaporation occurs over the oceans, but only 90% of the moisture falls back harmlessly over the ocean. The missing 40,000 cubic kilometers of moisture is transported from the oceans to the land each year, but that only accounts for 35% of all the rainfall on land. That's because 65% of continental precipitation is fueled by recycled moisture via evaporation from lakes and wetlands and transpiration by vegetation. Because the eastern U.S. has more wetlands and more forests than the West, it recycles more rainfall. During the warm months of June and July, about 60% of the eastern USA's rainfall is sourced from the recycled moisture. So the eastern USA should also be a very sensitive indicator of any global warming induced by increased evaporation and rainfall as suggested by Treubert. But in contrast to Treubert's theoretical pseudoscience, Nguyen's 2018 analysis shows that the eastern USA has not experienced any precipitation trends in 30 years. Now, depending on what model is used, results often differ. Nevertheless, Kazemzade's 2021 satellite analysis likewise found no precipitation trends in the eastern USA for the most recent 20 years. Now, using a different time frame, Kazemzadeh did find significant trends in different locations than Nguyen, but still only 6.1% of the Earth experiences any statistically significant increased precipitation, while an equal 6.1% experienced significant decreases. Both studies suggest no change in the supply of moisture for rainfall. In contrast to Treumbert's expectation of amplified precipitation where moisture converges, hardly any portion of the ITCZ's region experiences any increased rainfall. In addition to the effects of different starting dates for rainfall trends, how a region's boundary is defined also alters trend analyses. Because state agencies manage water resources, Nguyen 2018 analyzed rainfall trends by political boundaries, resulting in 10 states exhibiting insignificant trends of increasing rainfall, while 5 states experienced significant decreasing trends. A much different picture arose when he defined regions by the more climatically meaningful watershed boundaries. Such analysis then found no regions in the USA experiencing any increase in rainfall, but a significant drying trend in the Colorado River Basin. So beware, depending on a researcher's agenda, they can cherry-pick the statistics that best suits their narrative. If Treumbert's theoretical proclamations are true that global warming has increased extreme rainfall, it should be reflected in higher flood peaks in the rivers. To test the global warming claims, Gabriela Villarini examined 50 long-term stream gauge stations with at least 100 years of data. As her results here indicate, there has been no increasing trend in peak river flows. The range of flow volumes remains stationary within the bounds of natural variability for over 100 years. Nonetheless, there are always outlier years with damaging floods, and those years provide the misleading clickbait headlines for the media. Here, the oldest USA station that has monitored the Connecticut River since 1836 had a major flood due to the rains of the March hurricane of 1936. So damaging was that flood, it prompted the USA's Flood Control Act of 1936. Given the lack of any long-term river flow trends, Villarini concluded, it is easier to proclaim the demise of stationarity of flood peaks than to prove it through analyses of annual flood peak data. The causes of flood damage from hurricanes are more complex and must consider extreme precipitation, coastal surges, coastal landscape changes, and broken levees. But as expected, the devastating flood from Hurricane Katrina in 2005 provided Treubert and the media with the optics to push his single-minded obsession with the climate crisis. Again, he repeated that the Clausius-Clapeyron equation dictated worse floods due to an 8% increase in extreme precipitation from a warmer ocean, making Katrina stronger. But Katrina evolved as local conditions change, not as a global warming statistic change. Katrina was a small Category 1 hurricane when it first hit Florida, then evolved into a Category 5 over the Gulf of Mexico, but declined into a Category 4 and 3 as it hit the Gulf coastline. If we cherry-pick Katrina's time as a Category 5 hurricane, it rates as the 12th strongest in 150 years. But there were stronger hurricanes in the 1930s and 50s, contradicting claims that global warming had caused stronger hurricanes. The horrific flooding was not due to human effects on climate, but from humans who had degraded the landscape around New Orleans by altering the Mississippi River's course and draining and urbanizing the wetlands of its floodplains. Parts of New Orleans are now 3 to 5 meters below sea level. Even without a hurricane, any failure of its levees would produce a devastating flood. A recent study by Dixon in 2005 found that New Orleans is still sinking at a rate of 6.4 millimeters a year, and in some places as much as 33 millimeters per year. Sinking land is a far bigger threat than any sea level rises. Where hurricanes make landfall is primarily determined by how the winds from the Atlantic subtropical high pressure system guides the storm. Known as the Bermuda High when centered more towards the USA, the winds more often drive hurricanes into the Gulf of Mexico. Relative to times when the high is centered further east and known as the Azores High, which causes more hurricanes to pass up the middle of the Atlantic with little coastal impacts. The relationship between the high pressure system is clearly seen by mapping the frequencies of hurricane storm tracks. As represented by the dark red regions, hurricanes more frequently pass harmlessly northward, much to the east of the USA. The two regions that experience the most landfalling hurricanes are around New Orleans and the East Coast, from Florida to North Carolina. Climate scientists have been deeply divided on whether or not global warming is causing more Atlantic hurricanes. Scientists with Treubert's ilk point to a rising trend as seen in green. Other scientists argue before the satellite era, many hurricanes went undetected and thus were underestimated unless they came closer to shore. So those scientists have adjusted the data and find no trend as illustrated by the orange line. Hurricane landfall data is a little more robust, and it too finds no increasing trend. And accordingly, there is no significant trend in precipitation in the USA where it is most affected by hurricanes. High precipitation in every cyclonic storm, whether called hurricanes, extratropical cyclones, atmospheric rivers, or thunderstorms, is primarily due to warm moisture being transported poleward from the tropics by the warm conveyor belt. As the warm conveyor approaches colder air to the north, the moist air rises and cools, causing moisture to condense and rain out. The rising air of the warm conveyor also induces cold, dry air to sink from the upper atmosphere to maintain a mass balance. These dynamics of all cyclonic storms are readily seen in satellite photos. The long gold arrow illustrates the path of the warm conveyor that is causing clouds to form as it rises. Also note the faint outline of the USA showing that the moisture is being pulled from the tropics south of the Yucatan. The dark band paralleling the warm conveyor represents the cold, dry air that has descended into the cyclone. The Earth's more frequent atmospheric rivers transport more moisture poleward than the hurricanes. Likewise, via their warm conveyor belts, they transport more than 90% of all the tropical moisture that reaches the mid-latitudes. Globally, about 130 atmospheric rivers occur each year with 20 to 30 hour lifespans. Disproportionately, California averages 15 a year, explaining why California is such a hotspot for extreme precipitation. Globally, there can be 5 or 6 atmospheric rivers happening at any one time, but not all make landfall. Like hurricanes, the path of an atmospheric river is determined by the configuration of high and low pressure systems. Here, an atmospheric river extends poleward from the Pacific warm pool. With a contracted low pressure system centered around the Aleutian Islands, the atmospheric river was guided north of San Francisco, the green dot, and into the British Columbia on September 21, 2021. 1 month later, the low-pressure system had expanded and moved southward. Along with the high-pressure system to the south, the atmospheric river was guided into California. San Francisco received over 4 inches of rain in a single day, ranking as the fourth most ever recorded. But we can't blame global warming. More and stronger rainfalls happened in the cooler 1800s. The Great Floods of 1862 in California was caused by an atmospheric river rain-on-snow event in the Sierra Nevada that resulted in the downstream flooding of Sacramento. By studying the amounts of sediment delivered by heavy river flows into the Santa Barbara Basin and San Francisco Bay, scientists have identified floods caused by past atmospheric rivers. During the cooler times of the Little Ice Age between 1300 and 1860 AD, California experienced several atmospheric river-induced megafloods. The greatest of all in over 2,000 years happened in 1605. So why so many megafloods during the cooler Little Ice Age? The best explanation suggests as El Niños and La Niñas in the associated Pacific Decadal Oscillation alters the sea surface temperatures, the pressure systems align accordingly. Although debated, most researchers have determined that during the Little Ice Age, the Pacific Ocean existed mostly in an El Niño-like condition, with more rainfall over the eastern Pacific due to warmer surface temperatures. In combination with more atmospheric rivers initiating from a warmer eastern Pacific, the research by Joe 2019 shows El Niño-like conditions configure the cyclonic low-pressure systems and anticyclonic high-pressure systems to drive more atmospheric rivers into California. During La Niña-like conditions, the eastern Pacific is cooler and the western Pacific is warmer. This promoted more atmospheric rivers beginning in the western Pacific warm pool. And in combination with the resulting changes in pressure systems, more atmospheric rivers are guided northward into British Columbia, and California then becomes drier. Now, during La Niñas, the resulting warming of the western Pacific warm pool also promotes more atmospheric rivers flowing into the southern hemisphere, one which recently flooded Australia's Brisbane region. The configuration of pressure systems focused that atmospheric river onto Brisbane and its surrounding regions, bringing a record 24.1 inches of rain in just 3 days. But that is not the record rainfall for Brisbane's watershed. As has been the case so often, it was during cooler times that a stronger atmospheric river inundated the region in 1893. In the nearby town of Crowhamhurst, a record 35.7 inches of rainfall fell in just 1 day. So make no mistake, as experts have warned, megafloods are coming with the same devastating force as they always have in the past. Climate models might predict worse atmospheric rivers due to increased evaporation and the atmosphere's greater moisture capacity from global warming, but satellite data contradicts those claims, making forecasts based on global warming useless. And data from the Little Ice Age also shows atmospheric rivers are independent of global warming. However, on the good side, forecasting the location of devastating floods may be more predictable because the path of hurricanes and atmospheric rivers are modulated by natural oscillations and their effect on observable guiding pressure systems. But despite better weather forecasting, the real worry is most people continue to colonize more and more floodplains, putting themselves in harm's way. If you live in a floodplain, cutting your CO2 emissions won't stop the floods. The wisest plan is to move to higher ground or else keep reinforcing your levees. Up next, it's going to be part 8, the Antarctic Ice Cap. And until then, embrace renowned scientist Thomas Huxley's advice that skepticism is our highest of duties and blind faith our one unpardonable sin. And if you found and appreciate the science clearly presented here, science that's rarely presented in mainstream media, then please Give it a like, share it, copy the URL, and send it to friends. Subscribe to my channel, or read my book, Landscapes and Cycles, An Environmentalist Journey to Climate Skepticism. Thank you.